I'm Pete Garcin, and we're going to walk you through this TensorFlow-powered game AI that I built here. If you came by our booth, you probably maybe saw it or play it. So just really quickly about me, my name's Pete, and I'm dev evangelist at ActiveState, and you can find me online at GitHub and Twitter there. So really quickly, I want to talk about the workflow for working with TensorFlow and Go. Right now, the recommended workflow is that you train your models in Python first, so that's what we did here. So I have a Python version of this game as well, and I trained the model and exported it, and it uses the save model builder, and that will dump the TensorFlow model and all the weights and everything out to a protocol buffer, and then you can load that using the TensorFlow client in Go. So really quickly, obviously, you probably know what TensorFlow is, or if you don't, it's Google's library for machine learning, and expresses the calculations as a computation graph. So that sort of is important later. Has lots of language bindings, including a Go one now, and supports pre-trained models. So in addition to the one I trained, you can also download like an image recognition one and stuff. So data modeling is important for machine learning. It's not magic, so you still need to have a little bit of expertise to understand how to format your data. So I'm going to walk through that really quickly about how I formatted the data for this game and how we trained the AI. So this is what our AI's brain looks like. Our data model is basically the relative position and the relative velocity of our enemies to our little hero. And it's a really simple binary classifier which decides whether it should shoot at you or not shoot at you. And so we did it as a simple neural network. So just to show you, there's our little hero gopher and the little pulsating brain enemies. And you can see, so first two features are the difference in their x position, then their difference in their x velocity. And so then in the training mode, you can fly around randomly, and the enemies fly around randomly, and they shoot at you randomly. And if it logs a hit, then it stores it as a 1. And if it logs a miss, it stores it as a 0. Then it uses those data points to train the model. You need about 500 data points for it to be pretty stable. So some of our sample training data looks like this. So you see the difference in pixels stuff, difference in position and difference in velocity as pixel positions and pixels per second. But it's really important that you need to normalize your data. So it's normalized between 0 and 1, and they're in real-world units like per second things, because if you don't have that, then you might have some differences between the way that the game behaves in Python versus where you trained your model and in Go, so it's important that it stays consistent. So our network sort of looks like this. This is a little visualization tool that I built, and it shows the input features across the top and the output at the bottom. It basically shows the weights as the green and red lines in between, thicker lines, are stronger weightings. So it just gives you a little sense. I can't really go into how I decided on what the layers were. It was basically a little bit of trial and error until this was something pretty stable. So now we're going to load our model in Go. We've got our model, we've trained it, and we're going to load it. And we just use the TensorFlow binding we call load save model. Exported brain is a folder that it was exported from. And then there's a tag there. It's really important that you have the right tag. You can tag it either as a serving model or a training model. And so this one I had as a training model. So I loaded it. Now what? I was like, OK, now how do we make it work? How do we make it do something, right? So we need the operations, right? So it stores the mathematical operations as nodes in the graph, and so we need the operations for the input and output nodes. So we get the input node here by calling this graph operation and get the name of it, and graph operation to get the name of the output. So we have our two inputs. But like, how did I know what that was called, right? So this really was problematic for me, and yeah, this is totally not me looking through the raw protocol buffer. If you were smart, you probably would like print the names of them in Python before you exported it, but I maybe or maybe didn't look through the raw protocol buffer to find them. But once you can tag them in Python as input and output, and once you find the name of your input nodes and your output nodes, that's how you can access them back here by loading them, getting the operations. So now we want to make it think, right? So we need to execute the TensorFlow graph, and we do that in a session. So we What we do is we build, so you can see our inputs there, dx, dy, du, dv, and we put them in a new tensor, and then we run it through the session, and you can see our input and output operators there, and they're labeled in orange. And so then when we run that, we get results back. And the result that are returned as an array, but we only had one result, which is basically just a float. And so what we do is we have a boundary where we say, if it's less than a half, don't shoot. If it's more than a half, shoot. And that's their entire brain. So what it looks like is basically it converges on this strategy where if you were sort of in this forward cone of these enemies, then what will happen is they will shoot at you indiscriminately. And you can see them shooting at the little gopher there. But if you're not, if you're outside of that sort of cone, they won't shoot at you at all. And that basically is demonstrating that they have learned through the neural net when they can accurately find you and shoot at you, kind of thing. So yeah, so just really quickly here, a lot of people ask me what library I use. I use a library called Pixel. It's a pretty new library. It's got active development, great community around it. So I use that to do all of like the graphics, the rendering, sprite sheets, all that kind of stuff. And there are other game libraries out there for Go. There's a couple there listed, and hopefully many more to come, because there's actually a lot of opportunities to contribute to these communities, both on the ML side and on the game side. So there's obviously still a lot of both low-level, high-level tools if you work for both of them. Tools for doing games. The TensorFlow bindings could use contributions as well. There's still lots of work to be done there. Documentation, like for instance, so that you know how to find the nodes when you're using the TensorFlow binding and how to work with that. And there's a tool for Python called Keras, which is like a high-level tool for machine learning. It's really, really great and makes it really, really accessible to start building models. And Go could probably use its own version of something like that. And so really just in summary, data science, machine learning is a growing use case for Go. A lot of stuff for like this operationalized model where you are deploying it out with a pre-trained model. Game community is active and in its infancy, lots of opportunity to help out. And yes, this game will appear on GitHub, so follow me for updates. I'll put both the Python one that has a training mode and the Go one up there on GitHub, and hopefully people contribute and make it better, because there's lots of really obvious ways to improve this model. It's a very simple thing, but lots of ways to make it better. And so, yeah, thank you.